This research paper introduces a novel approach to graph anomaly detection, GAD, by leveraging the one-class homophily phenomenon, where normal nodes tend to have strong connections with each other, whereas abnormal nodes exhibit weaker homophily. The authors proposed Truncated Affinity Maximization, TAM, an unsupervised anomaly scoring measure that assigns larger anomaly scores to nodes with weaker local affinity to their neighbors. The proposed framework utilizes local affinity maximization-based graph neural networks, LAMNet, and normal structure-preserved graph truncation, NSGT. LAMNet is trained using a local affinity maximization objective on an iteratively truncated graph structure yielded by NSGT, reinforcing the strong affinity among nodes with homophily relations to their neighbors. This method avoids potential bias caused by non-homophily edges and enhances the effectiveness of GAD through the use of randomness in NSGT-BASED graph truncation to build a bagging ensemble of TAM. The authors demonstrate the effectiveness of TAM on 10 real-world GAD datasets, outperforming 7 competing models with a significant increase in AUROC, AUPRC. They also introduced 2 novel components, LAMNet and NSGT, to implement TAM. Figures 1a and 1b illustrate the one-class homophily phenomenon and local affinity distributions of normal and abnormal nodes on 2 popular benchmarks, Blog Catalog and Amazon, showing that TAM-BASED node representations offer well-separable local affinity scores between normal and abnormal nodes. The paper contributes to the field of GAD by empirically revealing the one-class homophily phenomenon, introducing a novel unsupervised anomaly scoring measure, and proposing TAM, which learns expressive normal representations by maximizing local node affinity on truncated graphs. This new perspective on quantifying the normality-abnormality of nodes enables simpler anomaly scoring than existing popular measures, providing a promising direction for future research in GAD. The research proposes a novel approach for learning anomaly discriminative node representations in graphs, focusing on maximizing local node affinity for unsupervised GAD. The Truncated Affinity Maximization, TAM, approach involves local affinity maximization networks, LAMNet, and normal structure-preserved graph truncation, NSGT. LAMNet learns a GNN-based mapping function to maximize node affinity with homophily relations, while NSGT removes non-homophily edges by truncating the graph based on node distances. The approach is optimized using an objective function that maximizes local affinity and adds a regularization term for distinguishability. Demonstrated on various datasets, TAM shows significant improvements in anomaly detection. The paper also presents an ensemble of TAM models to enhance robustness and experiments on 6 real-world GAD datasets, outperforming 7 competing methods in AUROC and AUPRC metrics. Additionally, it compares node representation spaces learned by TAM with competing methods, showing significant superiority. Here is a combined summary of the 4 pages. In the realm of graph anomaly detection, GAD, a novel anomaly discriminative property, one-class homophily, is introduced, which optimizes an anomaly measure on truncated adjacency matrices through a truncated affinity maximization, TAM, approach. This approach is demonstrated to be superior to 7 state-of-the-art, SOTA, detectors through extensive experiments on 10 real-world GAD datasets. The TAM approach is robust to camouflage attributes and performs well on large-scale graphs, but it has limitations, such as not handling primarily isolated nodes and requiring large memory for very large graphs. The paper provides a comprehensive survey of existing graph-based anomaly detection methods, focusing on attributed networks. It highlights key concepts and methodologies, emphasizing the importance of graph neural networks in detecting anomalies, as seen in works such as Oddball and Graph Contrastive Learning for Anomaly Detection. The authors discuss the role of heterophily in graph anomaly detection and its addressing, exploring the use of autoencoders and contrastive learning for anomaly detection. The paper acknowledges the need for further research, particularly in addressing inconsistencies in applying graph neural networks to fraud detection. The authors provide detailed explanations of key terms, equations, and algorithms, making it a comprehensive resource for researchers and stakeholders in the field. The paper's methodology is built upon optimizing an anomaly measure on truncated adjacency matrices, which is formulated as a maximization problem. The truncated affinity maximization approach is robust to camouflage attributes and performs well on large-scale graphs, but it requires large memory for very large graphs. Future work includes adapting the method for datasets with strong heterophily relations and optimizing performance for large-scale graphs. In the realm of anomaly detection on attributed networks, numerous approaches have been proposed to leverage the power of graph neural networks, GNNs. Researchers have developed various techniques such as the Graph Attention Network, GAT, and the Deep Graph Infomax, DGI, model to address the issue of homophily. The use of contrastive learning, as seen in models like the graph neural network with heterophily, GNNH, is also significant. Additionally, studies emphasize the importance of considering both node attributes and structural information. The field continues to evolve, with a focus on leveraging GNNs, contrastive learning, and specialized techniques for fraud detection and unseen anomaly identification. The authors investigate the one-class homophily phenomenon in graph anomaly detection, demonstrating it on 8 datasets. They argue that even in cases where the one-class homophily phenomenon is weak, it is still possible to remove non-homophily edges, resulting in a truncated graph with stronger one-class homophily. The homophily distribution of normal and abnormal nodes is visualized, showing a significant gap between the two distributions in most datasets. Here is the combined summary. The paper presents a novel anomaly detection method, TAM, and evaluates its performance across various datasets, focusing on its sensitivity to hyperparameters and time complexity. The results of AUROC and AUPRC demonstrate that TAM generally performs better with increasing ensemble parameter T, which reduces the impact of randomness in truncation. The addition of regularization improves the model's effectiveness for certain datasets, but not others, possibly due to attribute diversity. The time complexity analysis reveals that TAM's overall complexity is lower compared to existing methods. The anomaly scoring section highlights the benefits of using multi-scale truncation, which improves performance stability across datasets. A comparison between shared weights and non-shared weights LAM nets shows that shared weights can enhance performance in certain scenarios. The paper presents a comprehensive evaluation of TAM's performance across 6 datasets, comparing it with its variants and competing methods, including iForest, Anomalous, Dominant, HCMA, COLA, SLGAD, and COMGA. The results demonstrate that TAM performs consistently better or comparably well to its variants, and the ablation study highlights the superiority of the proposed NSGT method over the similarity cut method. The paper provides ROC and precision recall curves for TAM on the 6 datasets, showcasing its adaptability to different hyperparameters and efficient computational complexity. The comparison with existing methods highlights their differences and strengths, emphasizing the technical aspects and significance of the results. Overall, the paper highlights the advantages of TAM in anomaly detection, particularly in its adaptability to different hyperparameters and its efficient computational complexity, making it suitable for expert researchers and stakeholders. This research paper introduces a novel anomaly detection method, Algorithm 2 TAM, which leverages graph neural networks, GNNs, to compute anomaly scores for all nodes in a graph. Given a graph G equals V, E, X, the algorithm first computes the Euclidean distance between connected node pairs. It then initializes a GNN and truncates the graph at multiple depths, updating the graph structure. Subsequently, it applies LAM-net, a layer-wise anomaly detection approach, to each truncated graph. The anomaly scores are calculated using equation 2 and aggregated over multiple sets of graph truncation depths. The optimization process involves minimizing a loss function that includes both the anomaly scores and a regularization term to encourage diverse anomaly scores across nodes. The parameters are updated using stochastic gradient descent. This method offers a multi-scale approach to anomaly detection, enhancing its robustness and accuracy. The proposed TAM method demonstrates promising results in identifying anomalies in attributed graphs and provides a foundation for further research in this area. However, the current implementation of TAM assumes that the attributes of nodes are numerical, which may not be the case in all real-world scenarios. Additionally, the authors note that incorporating additional information about the network structure could further enhance the accuracy of anomaly detection.